Hello, algebra students. This lesson video is going to be on equivalent quadratic expressions, as well as what standard and factored form are. I've got the warm-up on the screen. Go ahead and pause the video now so you can try it, and then press play when you're ready to discuss your answer. The warm-up question asks you to explain why the diagram that below right here shows the area of 6 times 3 plus 4 equals 6 times 3 plus 6 times 4. I'm going to go ahead and give myself some space here to talk through it. Looking at the left side of this equation, we've got 6 times 3 plus 4. We're given the clue that we're talking about area, and if you remember from developmental math, when you're talking about finding area, we learned that area equals length times width. That's going to be a big part for this. So on this left side here, it's showing that in order to find the area of the rectangle, we would need to take 6, which is this length right here, times 3 plus 4. 3 plus 4 is going to represent this length right here. To get that total length, I would add 3 and 4 together. And so this one right here is just calculating the area based on what we know about length times width. It's finding that whole space right there. The second problem over here is breaking it into two multiplication problems. So that first one says 6 times 3. 6 times 3 wouldn't give you the area of the whole rectangle. It would just give you 6 times 3. It would just give you this area right here. But then it says plus, and it gives us another multiplication problem, 6 times 4. 6 times 4, I see the 4 right here. And if this top right here, this is 6, it means this is also 6, right? So 6 times 4 would be finding the area of the second rectangle right here. And so if I find the area of the yellow rectangle and the area of the purple rectangle and add them together, that's a different way to find the area of the entire rectangle. And so there's two different ways to find the area of this rectangle. You could just multiply length times width and use that 3 plus 4 to find that length, or you can do it in two sections here. Now you might be asking yourself, why on earth is this the warm-up? How does this help me with algebra? This idea of this area diagram is something we're going to use in this lesson with quadratics, and it's going to help us, similar to this, think about how you could find that entire multiplication problem. Our plan in this lesson is, like we just mentioned, to use diagrams, but also distribution to help us rewrite quadratic expressions. There's a couple words I want to highlight here just to make sure our brains are refreshed on what we are learning before we jump into the lesson. The first one is distribution or distributing. You've heard that before. What does distribute mean? To give you an idea using this problem up here with 6 times 3 plus 4, we said distribute is what you call it when you take something outside the parentheses and multiply it to what is inside parentheses. We've seen this a lot with variables, but you can also do it with numbers like this and say, well, 6 times 3 is 18 and 6 times 4 is 24. We call that specific multiplication distributing. So we're going to use diagrams like that one above with area and distribution to help us rewrite quadratic expressions. This word quadratic is super important. It's super important because it is the name of this entire unit. What is a quadratic? There's a lot of different pieces to that definition, but the one we've spent a lot of time talking about so far is a quadratic expression is going to be any expression that has a variable multiplied by itself in it. So you might see something like x times x somewhere in the expression, or you might see something like, well, x times x is x squared. So you might see x squared in the expression. quadratic expressions, in order to be a quadratic, it must have one of these things in it. So we are going to be using diagrams and distribution to help us rewrite these quadratic expressions. The other piece to this is we are going to write quadratic expressions in different forms. There are two types of forms that you see a lot when you talk about quadratics. And so we are going to learn the names of them and what it looks like when a quadratic is in each of those forms. That'll be the second half of this lesson. To get us started, though, we are going to start with these diagrams, similar to what you've seen on the warm-up, except now we've got some variables in them. So I'm going to, for right now, just put this first part on. Is this diagram here is how I would represent 4 times x plus 2. Notice when we set up the diagram, one side is 4, because one of the things I'm multiplying it by is 4. And then our other side, it's broken into 2 parts. One part is x, and one part is 2. That x plus 2 is what we use to represent this length here of the rectangle. Because there's 2 terms, the x and the 2, it meant I needed 2 parts to that side of the rectangle. When it comes to using this diagram to help you rewrite that expression, the reason we like this is because it shows the 2 multiplication problems we need to do. In order to get this answer right here, we took 4 times x, and in order to get the second answer here, we took 4 times 2. So just a different way to show that multiplication. Now looking at this expression here, is this a quadratic? Well, no, because we just said quadratics have this x times x or x squared in them. So this is not a quadratic, but we could use it for something like this. Now looking at this, I know this is a quadratic because it's got that n squared there. And even in this version of it with the parentheses, I still see that n times n. So I see n times n and n squared. I know these are quadratics. We can use this diagram above to set up this multiplication problem. When you go to set it up, I see I'm multiplying one term, so I need one thing on that side, by 2 terms. So this side here is going to have 2 parts. See if you can go ahead and fill in how we would label each side of the rectangle. Well, I'm going to multiply n, so I'm going to put n right here, times 2n plus 5. So that first term is 2n, and that second term is 5. When I get it set up like this, now I can see there's 2 multiplication problems we need to do. We need to do n times 2n, n times 2n, and then I'm also going to have to do, if this is n here, that means this is n. So I'm also going to have to do n times 5. So when you work out that math, n times 2n, well, n is like 1n, right? So 1 times 2 gives me 2, but then n times n gives me n squared. And then over here, n times 5, that's just 5n. So using the part I have in pink, that final answer would be 2n squared plus 5n. That's how you use a diagram for this. Now we've also learned problems like 4 times x plus 2 and even n times 2n plus 5. You already in class have been using distributing to help you with that multiplication. If I gave you n times 2n plus 5, you could distribute and say n times 2n is 2n squared, and n times 5 is 5n, and get the same answer using distributing. So to specifically name what we're doing here, we're seeing there are 2 options to changing n times 2n plus 5 into 2n squared plus 5n. Option number 1 is what you've already used up until this point, which is distributing. Distributing is that idea of taking what's in front of parentheses and multiplying it to what's inside. The second option here, this new option, is using a diagram. Some students are more visual learners than others. Visual means you like having pictures to help show what's happening with the math. And so this is a more visual way to see that multiplication. So there are two strategies we are using in this lesson. To help you practice with these two strategies, I've got two problems below. It says for each expression, use the distributive property or a diagram to write the equivalent expression. And if you get stuck, consider trying to draw the diagram we introduced here. What I will say is there's two problems. So I would encourage you, maybe try using distributing for one and try using a diagram for the other, just to help you get a little more familiar with both of those strategies. All right, I got us started by setting up the diagrams. Please know that there's multiple ways you can set up this diagram. So I've got mine kind of going long ways here, but you could also always set it up like this, where you put P up here and then the 4P minus 9 on the side there. Notice the 9 needs to be negative though, because we've got that minus sign there. So we have a negative 9. Either way you do this, you will get the same answer. So to give myself a little space, in order to find the equivalent expression here, I would want to do P times 4P. You can see that with the diagram, or if you were distributing, P times 4P would be 4P squared. And then we also would want to do P times negative 9. P times negative 9. And P times negative 9 is negative 9P. So your final answer for this first one, you would want to say 4P squared minus 9P. For our second one here, this one was a little different because we had 1, 2, 3 terms. So I need 1, 2, 3 parts on that side of the rectangle. But the multiplication is going to be the same. We need to do, I need 3 colors here, 0.5W times W, 0.5W, oh, look at this, I didn't finish my diagram, times W. That would give us 0.5W squared. We also are going to need 7 times W. I can see that 7 times W is 7W. And then we are also going to need negative y times w. I see negative y times w. And you can always copy your w down here too if that helps you. But negative y times w is negative yw. You can write negative yw. You can write negative wy. Those are the same thing. When you're multiplying two variables together, the order of those two variables can change, and it doesn't change the meaning. And so this final answer would be 0.5w squared. Since that's a positive 7, I'm going to say plus 7w and then minus yw. Or remember, you could say minus wy. In general, when I teach this in person, for these type of problems, most people like distributing. With distributing, we're familiar with it. You've seen it before with problems like this, 4 times x, 4 times 2. And so it's not too different to do it if there's a variable in front. The idea is the same. However, a lot more people like using these diagrams for this next part here, which is why we introduce them. In this next part, we're changing it up just a little bit. Instead of all of these problems where you're multiplying one term by 2 terms or one term by 3 terms, now we are going to multiply 2 terms, x plus 1, multiplied by another 2 terms, x plus 3. And so in order to do that multiplication, there's a little more happening, and the diagram really helps us see what those multiplication problems are that we need to do. There's going to be 1, 2, 3, 4 multiplication problems that I have to do in order to find the equivalent expression to x plus 1 times x plus 3. And with the diagram, you can see what those 4 multiplication problems are. in order to do x plus 1 times x plus 3, this box here tells me I need to do x times x. X times x is going to be x squared. This box right here shows me I need to do x times 3, and x times 3 is just 3x. This box here shows that I need to do 1 times x, and 1 times x is just x. And then finally, this box here shows that I need to do 1 times 3. 1 times 3 is 3. So the diagrams can help you keep track of those 4 multiplication problems you need to do, and it kind of keeps it all organized. Now, I will say these multiplication problems that I keep writing out, it is not necessary for you to write those. I'm just writing them down so you can see where these answers are coming from. If you only had x squared, 3x, x, and 3 in these 4 boxes, that would be perfectly fine because those are the answers. And so this diagram right here is showing me that x plus 1 times x plus 3 would equal x squared and then plus 3x plus x and plus 3. And you could write down those 4 terms in any order you want. You could do x squared plus x plus 3x plus 3. It's the same idea. Now, there is something we need to do here, and the question's giving you a clue. We are trying to prove that x plus 1 times x plus 3 and x squared plus 4x plus 3 are equivalent. And notice I don't have x squared plus 4x plus 3 written. Where do you think that comes from? Well, there's one final thing I can do with this expression. Notice this term and this term, those are like terms. So we could simplify this by saying, well, 3x plus x is the same thing as 4x. Remember plus x, there's that 1 right there. So 3x plus 1x is 4x. And so we get our final answer, x squared plus 4x plus 3. That is how you can use this diagram to help you with these more complicated multiplication problems. Now, just like before, you can also do this with distributing. So if I copy that problem one more time, x plus 1 times x plus 3. We can also do this with distributing, but sometimes it's a little harder to see what needs to be multiplied because there's a lot more here you have to multiply. With distributing, we've learned you multiply whatever is outside parentheses to what is inside. So in front, I have x plus 1. We're going to distribute that into 2 steps. We're going to first distribute the x and do x times x and also do x times 3. So just pretend the 1 is not there. We're going to distribute this x for our first step, but then we're going to distribute again, and we're going to take this 1 and distribute it. So do 1 times x and also 1 times 3. See with the arrows, you can see there's a lot more going on. There's a lot more multiplication, which is why more students, when it comes to these type of problems, might like the diagram because it helps us keep all of that multiplication organized. No matter how you do this problem, though, you will get the same answer. If I'm distributing, x times x gives me x squared. Next, we said x times 3 gives me a positive 3x. And then we've got 1 times x gives me 1x, or just x. And then 1 times 3 gives me 3. And just like above, we've got the same thing. So if you distributed it, you would also get the answer x squared plus 4x plus 3. This is going to be the last piece to finding equivalent quadratic expressions. Is a lot of times we are looking at our quadratic expression written more like this with 2 sets of parentheses, and we've got these 4 multiplication problems we need to do to find that equivalent expression. I'm going to leave this up here for a moment because there's one other thing I want to talk through, and it's how this would change if there were some negative numbers involved. So I'm going to adjust our problem just a little bit. I'm going to go ahead and erase all of this very slowly, apparently. And I want to think through, my goodness, there must be an easier way to do this. Yes, there is. No, there's not. I want us to think through how this would change if our problem looked like x minus 1, x minus 3. Go ahead, pause the video now and start thinking through how would the diagram change, how would the answer change, all of that. For x minus 1, x minus 3, the diagram would look similar in that I've got two terms, x minus 1, so I need two parts to this side, and x minus 3, I need two parts to this side. But the difference is, to show we're doing x minus 1 and x minus 3, I would need a negative sign here and a negative sign here. Now that wouldn't change this first multiplication problem. X times x is still x squared. But when we do x times negative 3, that would give me a negative 3x here. Negative 1 times x, that would give me a negative x here. But then negative 1 times negative 3, I'm back to positive 3 here. And so this would give me x squared minus 3x minus x plus 3, which would equal x squared minus 4x plus 3. So those negative numbers would just mean that when you're setting up your diagram, you want to make sure you show that pieces are negative. I want to go ahead and give you a chance to practice more with this. So below, there are 3 problems for you to try. Again, pause the video because getting that practice is super important. Pause the video, try these 3, and then come back when you have answers. For this first one, we can go ahead and set up the diagram. I've got 2 terms multiplied by 2 terms. So this side of my rectangle needs 2 parts, and the other side of my rectangle also needs 2 parts. So it'll look something like this. Notice x plus 1, it's the same for both of them. So I've got x and a positive 1. I've got x and a positive 1. That would be what our diagram looks like. When you go to do all that multiplication, x times x is x squared. X times 1 is 1x or just x. X times 1, same thing, x. Then 1 times 1 is 1. And so we are left with x squared plus x plus x plus 1. And that would simplify to x squared plus 2x plus 1. You should be getting the same information even if you did distributive property. For B, we've got 2x plus 2 times x minus 3. Again, you've got 2 terms, so I need 2 parts there, times 2 terms. So something like this, where one side is 2x and 2, and then the other side is x and that negative 3 there. I do want to mention, when you set up your diagram, it's okay if you have on this side the x and the negative 3. And then on the other side is where you put your 2x and 2. These will give you the same answers, I promise. The multiplication problems you might do in a different order, but it'll simplify to the same thing. And those multiplication problems that we need to do are 2x times x, which is 2x squared, and then 2x times negative 3 is negative 6x. 2 times x is 2x. And then 2 times negative 3 is negative 6. So that's giving me 2x squared minus 6x plus 2x minus 6. Again, you'd be getting that same information if you had used distributive property. And then this would simplify to 2x squared. Negative 6 plus 2 is negative 4. So we get negative 4x and then minus 6. For this final one, you have to think a little bit about what this means here. So I want to go back to what you know about squaring stuff. If I ask you what 3 squared is, well, 3 squared means 3 times 3. Or if I ask you what x squared means, x squared we said earlier at the beginning means x times x. If I ask you what smiley face squared means, it means smiley face times smiley face. Squaring anything just means you're multiplying it by itself. So if I'm asking you to square x minus 2, it means I'm asking you to multiply x minus 2 by itself. If we're doing x minus 2 squared, it means we are doing x minus 2 times itself, x minus 2. That is the first step to this problem. It is not as easy as saying, well, x squared is x squared and 2 squared is 4. That's not going to get all of the multiplication we need to do. We need to do x minus 2 times x minus 2. I've been doing diagrams for these first two, so let's look at what this would be if you use distributive property. You could also use a diagram. It'll give you the same answer. But with distributive property, just so you can see more examples, you're first going to distribute your x. So we would do x times x and x times negative 2. X times x is x squared, and x times negative 2 is negative 2x. Then we come in and we distribute again, this time not just 2, but negative 2. Make sure you're catching that negative sign there. That's another reason why the diagram can be really good, is it helps you see all the negatives. So negative 2 times x and negative 2 times negative 2. Well, negative 2 times x is negative 2x, and negative 2 times negative 2 is positive 4. So when we finish and go to simplify, x squared minus 2x plus 4. Be careful with that negative 2x and negative 2x. Those don't cancel out. A negative 2 and a negative 2 gives you negative 4. So that would be a negative 4x there. And our final answer would be x squared minus 4x plus 4. And these are 3 different examples of how you can use diagrams or distributive property to help you find these equivalent expressions. So to summarize, there are 2 methods we can use to help us expand these expressions. I haven't been using that word expand, but that is what we are doing here, where you're taking this problem and doing all that multiplication to expand and see those 4 terms. Those 2 methods, I keep mentioning them. Do you know what those 2 methods are? One way is you can distribute. You can do all of that multiplication that I have been doing with those arrows. Or our new way, the new way we've learned today, is a diagram. What's the benefit of each of them? Well, distribute, I would say the benefit is it's something you're already familiar with. We've been using distributive property since you all were in pre-algebra. And so that word distribute should sound familiar. You've seen a lot of examples of it. I think that's the benefit of distributing. I think the downside of distributing, especially for these ones we did at the end, is all of those arrows can start to get really confusing. And it's sometimes hard for students to see all the different multiplication problems they do, which leads me to the benefit of a diagram is you can see the 4 or more, because there could be more, multiplication problems. And I also think it's helpful with negatives. It means you can't miss a negative sign because you've got it right in front of the 3 right there when you go to do that multiplication. And so I think this can be helpful if you're getting really confused with the distributing or forgetting what you've already multiplied and what you still need to multiply. This keeps it a lot more organized. So I've got the question, do you have a preferred method? In the past, I've had students say, distributing all the way. I already know how to distribute. I want to do that. I've had people say, I'm going to do a diagram every single time now. I love how organized it helps me be. But I've also had a lot of students say, I think I'm going to use a mixture of both, right? These first problems we had been doing, like these look really similar to the distributing property problems we've already done before today. And so I've had a lot of students say for these, they don't feel like the diagram is necessary. It's pretty easy for them to see what they need to multiply. But when we start to do these more complicated problems, that's when they like to use the diagram. So I have also had a lot of students over the years say they prefer using a mixture of both. You just need to find what works for you. And the best way to do that is do lots of practice, do today's homework. And after doing more problems, you might be able to see, yep, I think I'm definitely a fan of this method. Related to all of the work we've been doing here with equivalent quadratic expressions, we said there are two forms you can see quadratics in. And those two forms are called standard form and factored form. Below, I have a bunch of examples. These are all examples of what standard form looks like. These are all examples of what factored form looks like. And these here are all examples of quadratics. But looking at these here, these quadratics are not in standard form and they are also not in factored form. The goal is you are using all of these examples here to answer these two questions. What are some characteristics of expressions in standard form? What are some characteristics of expressions in factored form? Pause this video for as long as you need and see if you can come up with a list of things you notice that everything in standard form has in common and everything in factored form has in common. And then using these here to kind of help you with that list as well. Like I said, pause the video and then come back when you're ready to check your answers. Starting with standard form, over the years, one of the first things students have noticed is that every single problem here in standard form, you see an x squared. Every single one. And that is definitely a piece of standard form. A standard form is always going to have that x squared in it. Now notice though, here under factored form, I see that exponent squared. And then under the neither column, I still see some stuff with x squared. So just because you see something with a squared or x squared in it doesn't automatically mean it's standard form. There's still more we can notice over here. Some other things people have noticed over the years about these examples in standard form is all of them have 1 to 3 terms. So for example, this one here has 1 term, this has 2 terms, this has 3 terms. Standard form always is going to have between 1 to 3 terms. So notice under the neither column, one of those things I had pointed out that had x squared in it does not have 1 to 3 terms. 1, 2, 3, 4, there's 5 of them there. So thinking about those 1 to 3 terms, one of the things you also might have noticed about all of these that's different for this one or even maybe this one is all of these are simplified. And looking over here at the ones that we said neither that had the x squared in, the problem with those is that they are not simplified yet. Standard form is always going to be simplified. And when you simplify it, you're putting together all of those x squares, you're putting together all of the x's, and you're putting together any numbers there. So for example, this one is not simplified because we could combine the 3x and the 3x. This one up here is not simplified and not in standard form because you would need to combine the 3 and the 4, and you would need to combine the 5x squared and the minus x squared there. Once you did that, then they would be in standard form. To summarize here, standard form is always going to have an x squared in it, always. And then when you simplify it, it might have a term with x and it might have a number as well. With standard form, those terms can be in any order. So a lot of the time, the x squared does come first, but notice here it doesn't have to be. Those are the main characteristics of these standard form expressions. You've got an x squared, there's going to be 1 to 3 terms in it, and it is simplified. When we come over to factored form looks a little different. And usually right away someone says factored form has parentheses in it. And you are right, it does. But again, notice over here in the neither column, there's a lot of things that have parentheses that are not factored form. So what makes all of these different from those ones I pointed out in green? Well, using the neither ones might help me figure out what all of these have in common. Notice here, we've got those parentheses, the x minus 3 times x plus 4, and then we're adding 5. Or here, we've got 2x times x minus 3, and we're adding 2. Here, we've got x plus 8 times 3x minus 8, and we're taking 4x minus all of that. Over here, notice we don't have any of that addition or subtraction. Factored form, that word factor comes from multiplication because all of these are multiplication problems and only multiplication. There is no addition or subtraction. One of the main characteristics is we are going to be multiplying something. Now, when you look a little closer at these, because we're talking about quadratics, specifically what is getting multiplied in there is an x times x, x times x. We've learned squaring this means you would be doing x times x, x times x, x times x, x times x. So that factored form is also going to have x times x somewhere in the multiplication when you go to do it. Those are the main characteristics of factored form, is that it's a multiplication problem and only multiplication, no addition or subtraction, and that when you go to do that multiplication, you're going to be multiplying x by x. So below I have the official definitions of these. Factored form is a quadratic expression that is written as a product, and we've learned product means multiplication. So other examples here of what you might see for factored form. And then standard form is a quadratic expression, and it's in the form ax squared plus bx plus c. That means there's going to be an x squared term for sure, and there might be an x term. So this first example doesn't have one, but we have one right here with the 3x, and then there might be a number. So we've got a -9 there or a -10. This is what we call standard form. And so earlier in this lesson, when we were doing all of this math to find these equivalent expressions, I was giving you something in factored form, and you were finding an equivalent expression in standard form. This is what we call factored form, and then this is what we call standard form. So that's the last piece, is putting that vocabulary to all of this math you have been doing. So the final question for you to help you see how you have done on this lesson is I want you to pause the video and try this question here, where the directions say write an equivalent expression in standard form. We learned 2 different ways you can do this. Feel free to choose whichever method you want, but your goal is to change these factored forms into standard forms. If you are able to do that, that means you did a successful job in this lesson. Go ahead, pause the video and try these now. All right, I'm going to do one with a diagram and one with distributive property. So if you wanted to set this one up with a diagram, I've got 2 terms by 2 terms. So I've got 2x and 5 times x and 1. That would give me 2x squared, 2x, 5x, and 5. So 2x squared plus 2x plus 5x plus 5. This right now is not in standard form because I need to simplify. So to finish, I would say 2x plus 5x is 7x, and still my plus 5. That would be our answer for this first one. For the second one, if you wanted to use distributive property, we would need to do x times x and x times 2. X times x is x squared, and x times 2 is 2x. And then we get to distribute again. Make sure you're distributing -2, -2 times x, -2 times 2. That gives me -2x and -4. And when I simplify that, I've got my x squared. 2x minus 2x, that's 0. 0x, that's nothing. So those do cancel out, and I just get x squared minus 4 for our final answer there. If you were able to do both of those, that is a definite sign that you are ready to go and can try the homework. If you had a little bit of a harder time, remember you can always join me for tutoring and we can do more examples of these. There's also lots of other videos online that you can check out as well. Thanks so much for watching this video and have an awesome day.